Let's jump right in. Welcome to this explainer on the absolute most profound cosmic detective story of our time, the search for planets beyond our solar system. For most of human history, the night sky was just this beautiful, static tapestry of distant suns. But today we know that nearly every single star you look up at hosts its own family of worlds. We call these alien worlds exoplanets. And the story of how we actually found them, and honestly, what they look like, it completely rewrites our entire understanding of the universe. Which brings us to the big one, the fundamental question that has literally driven human curiosity for centuries. Are we alone in the universe? It's the ultimate mystery, right? By studying exoplanets, we aren't just cataloging random distant rocks and gas clouds. We're actively hunting for the exact environments where life as we know it, or, hey, maybe life entirely unlike anything we know, could actually thrive. Okay, let's dive into this. Here is our roadmap. We are going to cover the exoplanet revolution, the birth of planetary systems, how we find them, a zoo of strange worlds, the habitable zone, and finally, the future of exploration. Part 1, the exoplanet revolution, from philosophy to fact. It's so easy to just take for granted that we know about thousands of exoplanets today, but turning this ancient, heavily debated belief into hard scientific reality, that was an incredibly difficult journey.
So let's look at the timeline. It actually kicks off way back in 1584. That's when the philosopher Giordano Bruno boldly proposed that stars were simply distant suns, complete with their own planets. Fast forward a few centuries to 1917, and an astronomer named Walter Sidney Adams records the spectrum of a star. We realize now that he was actually looking at the pulverized residue of a destroyed exoplanet. But, no one recognized what it was at the time. For decades, claims of exoplanets were just repeatedly discredited. It wasn't until 1992 that the first definitive planets were found. And strangely enough, they were orbiting a dead, spinning star called a pulsar. Then finally, in 1995, Michel Mayor and Didier Queloz confirmed the very first exoplanet orbiting a normal, sun-like star, 51 Pegasi b. That single discovery changed astronomy forever.
Part 2, birth of planetary systems, the cosmic forge. So, how exactly does the universe manufacture these worlds? You don't just magically go from an empty void to a complex solar system overnight. It all starts in these massive, freezing factories of gas and dust called giant molecular clouds. When a pocket of this molecular cloud collapses under its own gravity to form a brand new star, not all the material just falls straight in. It's because of a principle called the conservation of angular momentum. It's exactly the same physics that makes the spinning ice skaters speed up when they pull their arms in. The infalling stellar material basically flattens out and settles into this spinning halo around the infant star. We call this a protoplanetary disk. When we observe the HH30 protoplanetary disk, it's an incredible sight. It brilliantly illustrates the actual birthplace of planets. These disks are absolutely massive, stretching across tens to hundreds of astronomical units. And they're made almost entirely of gas, with just about 1% being solid dust. But here's the wild part. That tiny 1% fraction of dust, that is exactly where you and I come from. The formation of a planet is essentially this massive cosmic snowball effect. Step 1, microscopic dust grains rely on random motion to gently bump into each other and stick together. Once these little clumps reach about a kilometer in size, we call them planetesimals. At that point, they finally have enough of their own gravity to forcefully pull in more material. Eventually, these violently smash into one another, leaving behind massive planetary embryos that we call protoplanets. These bodies are so large and, honestly, so hot that they undergo internal melting. The heavy elements, like iron, sink right down to the core, while the lighter rocks float up to the surface to form a crust. Part 3, how we find them. The detective's toolkit. So we know they're out there, and we know how they form. But actually finding an exoplanet, that is a monumental challenge. To put it into perspective for you, a parent star is generally about 1 billion times brighter than the light reflecting off any planet orbiting it. It's literally like trying to spot a tiny fly fluttering directly in front of a blinding searchlight from miles and miles away. Because of that blinding glare, astronomers have to rely heavily on indirect methods. The two absolute heavyweights here are the transit method and the radial velocity method. The transit method is basically staring at a star and waiting for a planet to pass right in front of it. When it does, it causes this tiny, measurable dip in the star's brightness. Amazingly, this exact concept was actually suggested all the way back in the 1600s by Christian Huygens. Then you have the radial velocity method. This one measures gravity. As a planet orbits, it gently tugs on its host star, making the star wobble. We can actually detect that wobble as tiny Doppler shifts in the star's light spectrum. While transits and wobbles catch the vast majority of exoplanets, astronomers do have a few other brilliant tricks up their sleeves. We can occasionally use direct imaging, where we physically block out the star's glare using specialized instruments so we can see the massive distant planets hiding in the dark. There's also gravitational microlensing, which relies on a star's gravity acting like a giant cosmic magnifying glass for background light. We also use astrometry to track the incredibly precise physical shifts in a star's position. And finally, pulsar timing, where we measure the delayed arrival of radio waves caused by planets orbiting dead neutron stars. Part 4. A zoo of strange worlds beyond our solar system. Thanks to these incredible tools, and particularly the Kepler telescope, we've proven a breathtaking fact. There are actually more planets than stars in our galaxy. But what's truly mind-blowing is the sheer diversity out there. Our solar system? It is definitely not the standard template. The cosmos is filled with worlds completely unlike anything we have in our local neighborhood. Take, for instance, a Chthonian planet. The crucial point here is that a planet's proximity to its host star can be incredibly violent. If a massive gas giant, something like Jupiter, migrates too close to its sun, the intense stellar radiation can literally boil and strip away its entire thick atmosphere of hydrogen and helium. What gets left behind is just metal, an exotic super-dense husk, a scorched metallic or rocky core. And the taxonomy gets even wilder from there. We see ice giants composed of heavy elements like oxygen and carbon. We find mini-Neptunes, which surprisingly were the most common type of planet Kepler discovered, yet it's a size that literally doesn't exist in our own solar system. Theorists even propose swamp planets, completely waterlogged marsh worlds that might have totally unique ecosystems. And perhaps most haunting of all, rogue planets. These are worlds completely untethered from any star, cast out during the chaotic early days of their formation, just wandering in the pitch black of the galaxy, all alone. Part 5. The Habitable Zone, Seeking the Spark of Life. Now, of all the incredibly diverse worlds out there, these are the ones that really capture our imagination. By measuring a planet's transmission spectrum, basically looking at how starlight filters through its alien air, we can actually search for the molecular fingerprints of things like water vapor, methane, and oxygen. We generally focus our search on the Goldilocks zone. You've probably heard of this. It's the orbital band around a star where the temperature is just right, not too hot, not too cold, allowing liquid water to pool on the surface. But here is a super fascinating twist. Earth might not actually be the absolute pinnacle for life. Seriously, scientists have proposed the concept of superhabitable planets. These are worlds slightly larger than Earth, maybe with denser atmospheres, orbiting longer-lived stars. Theoretically, they could offer even more stable and nurturing conditions for biology than our own home planet. I want you to consider this number, 40 billion. Let the sheer scale of that sink in for a second. Based on Kepler data, astronomers estimate that there could be up to 40 billion potentially habitable Earth-sized planets orbiting sun-like stars and red dwarfs in our Milky Way galaxy alone. 40 billion chances for liquid water. 40 billion rolls of the cosmic dice for life. Part 6. The Future of Exploration, Reaching the Stars. Knowing these worlds are out there naturally leads us to our next great leap. Observing these worlds through telescopes is incredible, don't get me wrong, but to truly answer our deepest questions, we eventually need to go there. We have to make the massive leap from observation to actual interstellar travel. But of course, the big barrier here is the crushing reality of immense cosmic distances. As the astrophysicist Avi Loeb points out, human spacecraft right now are just too slow. The New Horizons probe, which is one of our fastest, travels at tens of kilometers per second. Even at that blistering speed, it would take 50,000 years to reach the nearest star, Proxima Centauri. To put that in perspective for you, if New Horizons had launched when the very first humans migrated out of Africa, it would only just be arriving there today. We desperately need a radical leap in technology. And that crushing reality is exactly what led scientists to the incredibly ambitious Breakthrough Starshot project. To solve the distance problem, scientists propose abandoning heavy chemical rockets altogether. Instead, you build a massive 100-gigawatt laser array right here on Earth. You then point it at a light sail, this ultra-thin membrane carrying a tiny payload that weighs just a few grams.
By focusing the intense laser light on that sail for a few minutes, you can actually push the spacecraft to a staggering 20% of the speed of light. At that speed, we could reach the Alpha Centauri system in just 20 to 50 years. That's well within a single human lifetime.
The journey from wondering if other planets existed to mapping thousands of them, and now literally plotting a course to reach them, it is an absolute testament to human curiosity. We've proven that the galaxy is teeming with worlds far stranger and more beautiful than we ever could have imagined. So, I'll leave you with this to ponder the next time you look up at the night sky. Among the billions of worlds scattered across the cosmos, could one of them be another Earth, or even home to another civilization? Thanks for joining me on this explainer, and keep looking up.